Okay, so we know how to work with position, displacement, velocity, and acceleration all now with vectors, and in more than one component or more than one direction. We have two-dimensional motion, three-dimensional motion. Let's talk about some two-dimensional motion or projectile motion. By definition, projectile motion only has acceleration in the y direction, and that's due to gravity, due to the acceleration of gravity. Okay, so what we saw previously was if we had some velocity vector, it could have some x component and some y component. It could have a k component too, but right now we're just shooting along a number line, but it's also going up and back down to the number line. So we have x and y motion. There's lots of things. If you drop a ball, if you throw a ball, it's projectile motion. If you shoot something out of a cannon or a gun, it's projectile. Doesn't matter which direction you shoot it, as long as something leaves with the velocity at some angle. So we're going to typically see some v naught. It's not a vector because I'm about to give you the angle. And in this case, I measure from the x-axis. We also learned that we could take this vector right here and figure out what each component is. So the x component was equal to v naught times the cosine of this angle over here, and the y component of the velocity is v naught times the sine of the theta. I wouldn't memorize cosine and sine unless you just know that it's in its typical orientation as measured from the positive x-axis. Otherwise, make a triangle, do a little Sakatoa action. No shame. Alright, so what can we do with this? Well, let's start by looking at just a regular old projectile. Let me get this out of the way. It's not letting me. So we'll come back to that. If I make an axis where this is x and this is y, and I'm going to shoot maybe a cannonball. It's going to have some initial velocity, call it v naught, and it'll be measured some angle theta from the x-axis. If we trace the path of this thing, we will get a parabola in space. So it's gonna look something like that, and it should be symmetrical unless we have drag, and I'll talk about drag, but that's just a form of friction. So it looks pretty symmetrical. We could call that the midpoint. Alright, what we need to observe in projectile motion is that there's only acceleration in the y direction. Oh, that was right, in the j. In the y direction. So, if there's only acceleration in the y, that means there's no acceleration in the x direction. We move at a constant velocity in the x direction. So we've got to memorize these facts. They're just little tidbits that we must know to be able to solve these problems. We can remember this can have a v naught in the x direction, some v naught in the y direction. Well, v naught in the x direction, like I just said, is going to be constant throughout the whole path of the projectile. V naught in the y direction is going to be under the influence of gravity. So it's going to have acceleration, right? And that acceleration is equal to g. lowercase g, the acceleration due to gravity. What I'm going to do here now is show you that if this had some initial v naught in the x direction that was that long, and I come over here and I plot a few different points, the magnitude of the x component does not change. If we consider drag, which we will, then it will change, but all of these have the same length. They also have the same direction because we defined it in the x direction. What we need to look at though is if this had some, let me make it blue, if this had some y component of velocity that looked like that, up here at the top it's going to have a 0 y component. It has to go to 0 so it can change direction. So the acceleration is causing the velocity to get smaller and smaller. Then it gets to 0 up at the top, and then it turns around, comes the other direction, and the acceleration pulls it back down to Earth. So the length of the final vector, if it landed on the same level it got launched from, should be the same. Just like this length and this length are the same, and this length and this length are the same. If it's shot from the same level it lands at, it will make a symmetrical parabola if not under the influence of drag. And so what we can see, I can resolve this final vector. Let's call this v final when right before it hits the ground. And this would be a negative theta. So it took off at angle theta, and this would be our theta right there. But if we wanted to measure this from the positive x-axis down like that, it would give us a negative theta. Okay. I wanted to take a look at this. I'm going to show a video of it too. This is someone dropping a red ball at the same time that a yellow ball gets launched to the right. So the yellow ball has some v naught like this. They're both released from rest in the y direction. This one is released from rest in the y and the x direction. We can see though that the acceleration due to gravity causes each ball to drop at the same rate. So this can be seen also if you take something like maybe you had a table and you're shooting a gun and we got a bullet. It's going to take a parabolic path. Well, if I had a device that dropped a bullet from that same level straight down, they would hit the ground at the same exact time, as long as the bullet was launched directly horizontally. And I got a video here I can show you too. Let me find it real quick. Here we go. So what this guy's doing is basically the thing with the bullet I just said, except he's not shooting a bullet.
Here we have two balls and also a device which is going to take both the balls and release them. One ball, however, is going to be hit by this piston when I release it, so that it has not only the motion of dropping from the surface, but also a motion in the x direction out this way. If I go ahead and put this ball on here and pull this up, this ball will drop straight down. And this is the ball that's going to have a motion also in that x direction. So let's watch the ball's motion, see what happens. And the question to ask yourself is, which ball is going to hit the ground first?
Which hits the ground first? Same time. Alright, so a little verification. That's something I would do in person for you. You can do it yourself though too, if you maybe like put a marble on the countertop and flicked it at the same time as you dropped one. You really want something that releases them both at the same time. I just wanted to point out another cool little thing. Figure 411 in your book. It has some sort of ceiling. From that ceiling is a device that can release like a Coke can or can of soup or something. And there is someone down here at the bottom with, they say, like a blowgun, or it could be like a bow and arrow or something, right? Let me make that. So here's our arrow. There is our feathering on the arrow. Okay, when they shoot this, if gravity did not act on it and you lined directly up with the can, it would hit the can, right? But gravity does act on it and it takes a parabolic path. So it doesn't go quite as high as you would go if you shot it in space, where it doesn't take a straight line trajectory, it takes a parabolic trajectory. Comes back down to Earth eventually. Well, here's the cool part. If we dropped this at the same time as this, we will see, since they were both under the influence of gravity for the same amount of time, that they are actually going to hit. So as this takes a parabolic trajectory, at that time it's going to be a little bit lower, some delta y, than where it would have hit with a straight line trajectory. But guess what? That's exactly where the can would be. So if we released it from 1 and let it fall to 2, but it released at the same time as the arrow was shot with some velocity, then they still hit because they are both under influence of gravity for the same amount of time. Alright, just a cool little thing I saw. Alright, I'm going to continue this projectile motion and let's get some more equations of how we can solve problems.